Hello everyone, my name is Erin and today we're going to be talking about action potential. Action potentials occur before each muscle contraction. So this is a neuron in its resting state where the resting membrane potential or RMP is at negative 70 millivolts. This membrane potential is set by the sodium-potassium pumps that are lined throughout the membrane. 3 sodiums move out while 2 potassiums move in. This is why the RPM is more negative. I wanted to show this picture and label the parts of the neurons before we continued. The section in the blue is the dendrites. The dendrites receive the signals from the other neurons and help with neuron-to-neuron communication. This is the receptive segment of the neuron and helps with the binding of neurotransmitters released from the presynaptic neurons. An example of a neurotransmitter that does this is acetylcholine. This also helps with the production of graded potentials. The orange segment is the axon hillock that functions as the initial segment. It is responsible for the summation of graded potentials. This is when many small changes in the neuron's membrane are added to determine if the neuron will fully send the action potential. The conductive segment takes up the full length of the axon where action potentials are promoted. The axon terminals, where the action potentials can release neurotransmitters, make up the transmissive segment. There are 2 kinds of postsynaptic potentials that can be created within the neuron. Excitatory postsynapses make the potential less negative, giving it a greater chance of actually sending the signal. Inhibitory postsynapses do the opposite and become more negative and less likely to fire off. Now we're going to talk about something called the all or none law. This is the idea that a muscle fiber will respond to the stimulus completely or not at all. Now we're going to get into the individual steps described in the chart we see here. A stimulus causes the first movement we see in the chart. It causes the membrane to reach the threshold membrane potential, which is negative 55 millivolts. The example I used is like a child putting their hand on a hot stove where the pain is the stimulus. This moves us into the depolarization phase. Here, voltage-gated sodium channels open and sodium rushes into the neuron, making it more positive, which we can see in the chart as it spikes. Moving on to the repolarization phase, due to the new difference in the membrane potential, when the sodium channels close and potassium channels open to help return the RPM. Potassium moves out of the cell, making it more negative. The final step in this cycle is hyperpolarization. After the potassium channels close, there is a little bit more potassium within the neuron than there was when it was resting. It is brought back to the RMP through the sodium-potassium pumps. There are some periods called refractory periods where the neurons are least likely to be involved in any more action potentials. Absolute refractory period means that there is absolutely no way that the neuron will engage in any other action potentials. Shortly after, the relative refractory period is able to happen, but the stimulus would have to be much stronger than regular. Whether or not the axon of the neuron is myelinated can cause some differences within action potentials as well. The 2 differences are continuous conduction or saltatory conduction. Continuous conduction is obviously continuous in its flow of steps because it is unmyelinated. But saltatory conduction happens when myelinated neurons and jumps between the nodes, as we can see in this picture. Now the action potential is over. Calcium channels help with the release of neurotransmitters like acetylcholine. This picture shows acetylcholine leaving the transmitting neuron and entering the receiving neuron. And that is my video on action potential.